Hey folks, welcome to another episode of Java. Today we're going to be talking about thread priority in Java. But before we dive into that, let's take a moment to understand what a thread is. In Java, a thread is a lightweight process that allows you to execute multiple tasks simultaneously. Think of it like having multiple chefs in a kitchen, each working on different dishes at the same time. Threads allow you to do the same thing in your Java programs. Execute multiple tasks simultaneously and efficiently. But in order to manage all of these threads efficiently, the Java scheduler needs to determine the order in which they should be executed, and that's where thread priority comes in. In Java, thread priority is represented as an integer value ranging from thread, min priority 1, to thread, max priority, 10, with the default priority being thread norm priority 5. Now that we understand what thread priority is, let's talk about how we can set and get the priority of a thread in Java. Setting the priority is really simple. All you have to do is call the setPriority method of the thread class. This method takes an integer value between 1 and 10 as an argument and sets the priority of the thread accordingly. For example, if you want to set the priority of a thread to the maximum value of 10, you would use the following code: thread setPriority thread max priority. Getting the priority of a thread is just as easy. All you need to do is call the getPriority method of the thread class. This method returns the current priority of the thread as an integer value between 1 and 10. So if you want to retrieve the priority of a thread, you can use the following code snippet. Let's talk about a scenario where you might want to use these methods. Suppose you're developing a Java application that has multiple threads, and you want to ensure that the most important tasks are executed first. In that case, you can use the setPriority method to set the priority of the most important threads to a higher value, such as 8. But you also need to be prepared for potential errors, such as if you accidentally try to set a priority value that's outside the allowed range. That's where the try-catch block comes in. By using this block, you can handle any potential illegal argument exception that may be thrown and provide a useful error message to the user, like the one shown in the code snippet above. So by using the setPriority and getPriority methods along with a try-catch block, you can effectively manage thread priority in your Java application. Now that we understand thread priority in Java, let's dive into the exciting world of multithreading. Multithreading is a programming paradigm that allows multiple threads to execute concurrently within a single process. A thread is the smallest unit of execution, and multithreading enables a program to perform multiple tasks simultaneously, thereby improving efficiency and responsiveness. Moving on from thread priority, let's explore the advantages of multithreading in Java. The first advantage is enhanced efficiency and responsiveness, which we'll see in action in this code example. As we saw in the previous code example, multithreading enables multiple tasks to execute concurrently, which can greatly improve overall performance and responsiveness. This is especially true for tasks that involve I/O operations such as downloading files or processing user input. Let's take a closer look at this code example to see how multithreading can be used to handle these types of tasks efficiently. In this example, we have two threads, one for downloading a file and another for handling user input. By creating separate threads for each task, we're allowing the program to execute both tasks concurrently without one task having to wait for the other to complete. This can greatly improve the responsiveness of the program, as the user input can be handled immediately while the file download continues in the background. Advantage. Another great advantage of multithreading is improved resource utilization. Unlike processes, which each have their own memory space, threads share the same memory space, allowing for more efficient use of available resources, especially in tasks that are CPU-bound. In this code example, we have two threads that are performing different calculations. By running these tasks in separate threads, we're allowing the CPU to execute both tasks efficiently, utilizing available resources more effectively. Because the threads share the same memory space, there's no need for the CPU to constantly switch between memory spaces, which can lead to wasted cycles and decreased performance. Another advantage of multithreading is that it can greatly enhance the user experience of a program. By allowing tasks to run independently, multithreading prevents the user interface from becoming unresponsive or blocked, providing a smoother and more responsive user experience. Let's take a look at this code example to see how this works. In this code example, we have a long-running operation running in a separate thread, while the graphical user interface is continuously updating in a while loop. This allows the user interface to remain responsive even while the long-running operation is running in the background, preventing the user interface from becoming unresponsive or blocked. This is a great example of how multithreading can be used to enhance the user experience, providing a more responsive and interactive application for the user. Finally, multithreading provides a structured and manageable approach to handling concurrent tasks, simplifying complex applications. In this example, we have a web server handling multiple requests, each in its own thread. By using threads to handle each request, the program is able to efficiently manage multiple concurrent requests without having to manually juggle them or implement complex synchronization mechanisms. This makes it easier to develop and maintain complex multi-threaded applications. So now that we've seen some of the advantages of multi-threading, let's dive into how we can actually create threads in Java. There are two main approaches: extending the thread class or implementing the runnable interface. The first approach, extending the thread class, involves creating a new class that inherits from the thread class and overriding the run method. This is the most straightforward approach, but it can limit the flexibility of your code since you can only inherit from one class in Java. The second approach, implementing the runnable interface, allows you to create a class that implements the runnable interface and provides an implementation for the run method. This approach is more flexible because it allows you to pass the runnable object to the thread constructor instead of extending the thread class directly. In both cases, you need to call the start method on the thread object to start the thread's execution. Let's move on to an even more important topic: thread synchronization. When we start two or more threads within a program, there may be a situation when multiple threads try to access the same resource, and finally, they can produce unforeseen result due to concurrency issues. For example, if multiple threads try to write within a same file, then they may corrupt the data because one of the threads can override data, or while one thread is opening the same file at the same time, another thread might be closing the same file. So there is a need to synchronize the action of multiple threads and make sure that only one thread can access the resource at a given point in time. This is implemented using a concept called monitors. Each object in Java is associated with a monitor, which a thread can lock or unlock. Only one thread at a time may hold a lock on a monitor. To give a step-by-step explanation, let's walk through each line of the code. Line 1 defines a counter class with a static int variable count. Line 2 defines a method increment, which increments the count variable. Line 8 defines the myThread class, which extends thread and overrides the run method. Line 15 starts two myThread objects, T1 and T2. Line 16 joins both threads to wait for them to complete before printing the final count. Line 18 prints the final count, which may be inaccurate due to the race condition that occurred during the unsynchronized access to the shared count variable. By adding the synchronize keyword to the increment method, we can ensure that only one thread can access the method at a time, preventing race conditions and ensuring that the shared variable count is updated consistently. In our examples, we saw how using synchronization prevented race conditions and produced predictable results, while not using synchronization led to unexpected behavior. And let's explore the lifecycle of a thread and the various states that a thread goes through during its execution. A thread goes through various states after its creation. It involves runnable, running, blocked, and terminated. These are the following states. 1. New. At the time when a thread object is defined, it is said to be born and ready to execute. It begins its life from this state. A thread can be created using the thread class and runnable interface. From this state, it is ready to move to a runnable state by calling the start method. The runnable state is where a thread may start executing at any point in time. Until it gets the CPU, it waits in a queue of already waiting threads. The thread with the highest priority would get the CPU first, and if all the threads have the same priority, they would execute in a first-in, first-out fashion. It is also possible to invoke a particular thread among the same priorities using the yield method. When a thread is allocated CPU time and is executing its assigned task, it is said to be in the running state. From the running state, a thread can transition to the suspended, blocked, or terminated states. The blocked state is when a thread is waiting for some resources or for other threads to perform their tasks. The sleep and wait methods can put a thread into the blocked state. It is possible for a thread to transition back to the runnable state from the blocked state. A thread can also enter the blocked state if it issues an input-output request to the CPU. in which case the CPU will put the thread to a blocked state until the request is fulfilled. When a thread finishes its task or is forcibly killed due to some error or event, it enters the terminated state, which is the last stage of its life cycle. The code first defines a task thread class that extends the thread class and then defines its run method, which demonstrates the different states of a thread lifecycle. The run method contains statements that represent the different states of the thread lifecycle, such as starting runnable, blocking, blocked, resuming, runnable, executing running, and terminating terminated. Next, the code defines the main class, which contains the main method that creates a new task thread object and starts it, causing it to transition from the new state to the runnable state. The main method then prints a message to indicate that it is waiting for the task thread to finish its execution. After that, the main method calls the join method on the task thread object, which causes the main thread to wait for the task thread to terminate before proceeding. Once the task thread is terminated, the main short method prints a message to indicate that it has finished. After that, the program execution is complete, and the program terminates. The code successfully demonstrated the different states of a thread's lifecycle in a multi-threaded program using Java's thread class and its methods. As we can see from the output of the code, the thread transitioned through various states during its lifecycle, taking a total of 12 seconds to terminate. The thread first transitioned from the new state to the runnable state, then became blocked, followed by runnable again, then running, before finally transitioning to the terminated state. The main thread waited for the task thread to finish execution using the join method and printed a message to indicate that it had finished. Let's now take a closer look at the methods that are used to control and manipulate the thread's behavior, as depicted in the diagram. 1. New thread start transitions the thread from the new state to the runnable state, initiating its execution. Stop. Deprecated method for forcibly terminating a thread. Avoid using due to potential risks. 2. Runnable resume. Resumes a thread that was previously suspended, rarely used. Run contains the code to be executed by the thread. Yield temporarily pauses the current thread, allowing other threads to run. Stop. Deprecated method as mentioned above. 3. Running sleep. Pauses the thread for a specified time, moving it to the blocked state. Wait. This method is used to release the object's lock and block the thread until it is notified by another thread. The thread will be moved to the waiting state until it is notified or interrupted. This method is typically used in conjunction with notify and notify all the methods to implement inter-thread communication and synchronization. Blocked. Resume. This method resumes a blocked thread, but like the resume method in the runnable state, it is also rarely used in practice. Notify. This method is used to notify a waiting thread on the same object, potentially moving it to the runnable state. This method is typically used together with wait to implement inter-thread communication and synchronization. Stop. Deprecated method that should not be used. That covers all the methods in the blocked state. Moving on to the next state in the thread lifecycle, which is the terminated state. In this state, a thread has finished its execution and can no longer be started or resumed. There are no methods associated with this state as it is considered the end of the thread's lifecycle. Thanks for taking this journey with me. We've covered a lot of ground in our exploration of thread lifecycle and methods in Java. I hope you've found this discussion informative and engaging. As we close, let's take a moment to appreciate the learning we've accomplished together and reflect on how this knowledge will help us become better Java developers. I'm always here to answer any questions you may have about Java or programming in general, so don't hesitate to reach out. Thanks for joining me today. You've been a fantastic audience. See you next time.